Yes, yes. 1 second. We just have to start the recording. You can
Sure.
start. Thank you.
All right. Thanks a lot. I'm very happy to present over here to such a broad audience working at the intersections of machine learning and natural sciences. I mean, the work that I'm mainly going to discuss is on the phase diagram of the thinnest possible layer of water, which is just 2D water, 1 molecule thick. But this is part of a bigger, grander goal that I have, or towards first principle simulations with a with some modern approach. And so just to introduce myself, is so this is basically my time evolution or my timeline, and I did my PhD with Michele Ceriotti in EPFL, and since 2020, late 2020, I'm a research fellow at University of Cambridge. And throughout my time, actually, I have been working and at various aspects of atomistic simulation, starting with enhanced sampling of rare events in chemical reactions, and then going towards simulate incorporating quantum nuclear effects and using machine learning potentials. And with Angelos Michailidis at Cambridge, I've been working towards getting high-end electronic structure methods to work for bigger systems. And most recently, I've started venturing into some multi-scale approaches. And I'm actually I'm very happy that I have had the opportunity to actually combine all of these methods in the last 1 year, where some nice work has come out. These are some of the these are three of my favorite works and I will be talking mainly about this one today. So just to make things clear, I mean, we talk about first principles. So what exactly are these? Well, I mean, you can think about simulations in two ways without invoking any of the technicalities. And the first step is to say, well, for a given potential energy surface, what are the energy levels of my system? So if you can enumerate all of them in theory, and in the second step, if you can ask, well, I mean, given that there are so many states, which of these are actually accessible in an experiment or at a given thermodynamic conditions? So if you combine the information of these two, you will be able to predict any experimental observable for systems that obey quantum mechanics. And so basically the groundwork and theory is already there. All we need to do is find some computational approaches to go from here to there. uh, this is a completely phenomenological approach, which basically means that the errors that we will eventually have in modeling an experimental variable would be in the errors in our model. So whether we solve quantum mechanics at a weak level or if we don't perform our sampling well, these will lead to errors in our modeling. A totally different approach is a purely inductive approach where we provide ourselves with some sort of information beforehand and we try to learn by example. So basically, if you have a database of a large number of molecules or large number of systems, and on the other hand, a database of large number of observables, there should be a one-to-one mapping between this and that. Given that there already exists something phenomenological, there has to be a purely inductive way as well, right? So this is just to say that with induction, the problem will be that whatever you predict will be based on what you know. So if you want to do an extrapolation, you have to be very careful in this case. So this is just to know what kind of methods we use and what should we be aware of in terms of errors. So one of the things which is generally used and something that I also do is to use something in between where you learn the potential energy surface of your system by example, basically by training a model. And after that, you do your statistical mechanics, which is incorporating the motion of all the atoms in a proper rigorous way. And thereby you get the best of both worlds, at least in this case. Yeah. All right, so let's get back to nanoscale water. Something about water is something I've worked on for a while since my PhD. And with Angelos, we decided to study what happens to water when you really confine it between very narrow pores. And the reason this topic is important is because we actually know a fair bit about water. Yes, there are open questions, but from a purely engineering or industrial perspective, where we would be probing maybe this part of the phase diagram, we know how the density changes. We know exactly how much water will expand upon freezing, where it will have a maximum in its density, and so on. Unfortunately, the same is not known for water when it's trapped inside, let's say, living systems, or when water is found between rocks, or water trapped in concrete, which gives it some very nice structural properties, and so on. Even basic questions like what is the phase of water when it's trapped between a membrane, these things are not clear. And hence, there is a need to understand all of that. The other thing why it's important is, for example, if we take a fuel cell where there is a semi-permeable membrane where water and aqueous ions can pass through. So our limited understanding of how water flows or what exactly is the phase or how we can tune its motion is really one of the factors which limits the production of high energy density energy materials. So again, not just for fundamental knowledge building, but there are also a number of practical examples on why water should be understood at the nanoscale. Another example would be for something we would use every day, which is water filtration, where nanoporous carbon is used. You can think of in future people will be using, let's say, graphene based filters, and in that case also you would need to know how does water behave at the interface so that you can really optimize for these properties, right? So limited number of experiments, pioneering, because you can already understand how difficult it must be to just probe a nanometer scale region, and understand properties of matter. But these experiments have shown that the properties of water are actually exceptional. For example, it's a complicated plot, so I'll just tell you, let's look at this. What it shows us is that based on the diameter of your carbon nanotube, your melting temperature can be as high as 440 Kelvin, which is greater than the boiling point of water in bulk. So that just tells you when you confine things in small regions, you will really have exceptional phase behavior. The other very nice example is the dielectric constant, which shows that nanoscale confinement can also tune your electronic properties. Is that bulk water actually, when you start reducing the thickness of your layers, it will reduce its dielectric constant, and after a certain point, the dielectric response will be same as the optical limit of water, which means that there is no vibrational contribution at all. So again, this is a very interesting experiment which tells us how just pure topology can actually change the behavior of water. And finally, one of the other things is the flow of water, which is experimentally studied, which shows that water flows very fast through HVN and carbon-based nanotubes, much faster than what it would do in bulk if you just look at water flow. And all of these just open the door to a lot of future technologies. Yeah. So our goal is to try to understand and also control these properties, right? So in this case, so this is kind of what we are going to simulate. It's more of an artist impression of our system, because the real system is of course not as funny. But what we really want to simulate is the smallest possible layer of water, one molecule thick between two graphene sheets. Again, the reason why we want to choose this experiment is because we want to choose this system is because experimentally it is possible to make measurements, and in fact people have found some interesting phases of water when trapped in between two graphene sheets. Of course, within our model, what we really try to do is we don't really account completely for the graphene. We want to ask a simpler question, which is when water is in topological confinement, which means that if there is a model potential which confines water to 2D, how do things change? And this itself, it has been a topic of a lot of studies. Unfortunately, even though there have been many force field and density functional studies, there wasn't really any consensus on what exactly is the phase behavior of water. And for instance, there are many force field studies where simulations have been performed at finite temperature, so the actual phases have been explored, and the results are really dependent on the water model. For example, certain water models will only give you square or rhombic phases. In fact, most of them at finite temperature only give you two of these phases. Uh, the order of the phase transition is not clear. Certain force fields give you a second order phase transition, which itself is a very interesting prospect, thinking just about thermodynamics and melting. And finally, if you look at just melting temperature of water, they can vary between 300 and 600 depending on which water model you choose. And again, this is not surprising because these water models are generally trained on experimental data for bulk, and these perform really well for bulk, but there is no real reason why they should do equally well in nanoscale confinement. And because there is no experimental data, it's hard to create these. On the other hand, you have density functional theory based calculations, which are generally restricted to 0 Kelvin due to their very large cost. And in these cases, this is in principle a first principles approach. But of course, in practice, you have dependence coming from your exchange correlation as well as your van der Waals terms, yeah, which model long range interactions. And depending on which setting you use, you can get different types of phases like a hexagonal, pentagonal, square, or rhombic. Or if you choose a different model, you can just get a square phase. And that is just because the energies of these are extremely close, and any error in DFT really propagates onto the phase diagram. And finally, because of the large cost, there have only been a handful of dynamical simulations, which means that the phase behavior hasn't really been explored properly. All right. So what I've really worked on is try to get the best of the two worlds by using machine learning potentials. And basically, my experience of machine learning potentials has really been towards crystal structure prediction type applications, where during my PhD and independently with Edgar Engel at Cambridge, we worked on one-shot machine learning potentials for, let's say, polymorphs of molecular crystals like benzene, glycinic, succinic acid, where we use a lower level theory like tight binding to generate our data, and then some data driven approaches to automatically select our training set. And this has really worked very well, and we have been able to get extremely good agreement with experimental data on known relative stabilities. For this work, however, we use something called an active learning scheme, and something which is also the theme of this the theme of this nice workshop. And so I don't think I have to explain this, but the idea really is that we wanted to study the entire phase diagram. So what we did was that we iteratively trained a model by starting from a bulk model, tried to study some interfaces. Then we had a model which was able to work for a monolayer of water, which was only stable up to say 300 Kelvin and 1 GPa pressure. And then we subsequently kept selecting points which had the highest amount of error or uncertainties, kept doing DFT on them, kept exploring our phase diagram, again kept picking points. And we needed like 4 iterations to select data, and after these 4 iterations, we were able to run simulations over a large temperature and pressure range as desired. And just to show you, this is, for example, an outcome in just 2 weeks. Me and Christoph Schan, one of the co-authors on this paper, we were able to go from a bulk water model to something which works for a monolayer of water. And at the end, since we were using active learning and we were trying to probe the entire phase diagram, we also had a proper validation plot where we see exactly the energy and force errors at every point on our phase diagram. And of course, when this model was ready, we actually calculated 10 points at every condition at DFT level, just to be really sure that we are getting the right energies and forces. And overall, we were very satisfied that in just 2 weeks, we were able to get a model which works, which has very low total force errors and so on. So that was extremely satisfying. Uh, and just to give you an expose of how fast this model was, for example, I performed something called random structure search. And this is basically a global optimization approach in some way, which allows you to find the metastable ice phases in 2D. And there have been some previous studies on this, with DFT uh, some years ago, which were pioneering in nature. But I was able to replicate all of these results on my workstation within just 24 hours. So basically, I ran the calculation, went home. Next morning, I recovered all of these phases, but I also found a new phase just like that. So this is just the power of a machine learning potential, which really expedites exploration of configuration space. So just to completely summarize the entire workflow, because there were many steps and I won't be able to go into all of the details. The first step that we actually did was not to train the machine learning potential, but we used high-end electronic structure, particularly quantum Monte Carlo, to perform certain total energy and force calculations on known phases of 2D ices. And that gave us some benchmark points, because quantum Monte Carlo is basically as good as it can get in terms of total energies. We use that to benchmark over 30, 40 density functionals, and we selected the single most important functional, which gave a good agreement with high-end electronic structure theory. And then we developed a machine learning potential for that based on the active learning approach that I discussed a slide before. In the third step, we performed random structure search, again, as I've pointed out, just to know what are all the metastable phases possible for 2D ice. And finally, once we had all of these phases, we wanted to compute their free energies and predict their the thermodynamic stability uh, at finite temperature and pressure to get the full phase diagram. And this is something which I've been working on since my PhD. And that gives us the entire phase diagram. So the first step basically allows us to ensure that our potential energy surface is accurate. The second step gives us the efficiency, to run long simulations. The third step allows us to be sure that we have really probed all the configurations of ice and we know that we are sampling all of the metastable phases. And the fourth step, we rigorously account for finite temperature, uh, finite pressure, thermal expansion, as well as basin volumes and configurational entropy in our phase diagram. And that hopefully gives us a predictive phase diagram. And just to be clear, again, just to specify which system we studied, this is, let's say, a lateral view. and we have a single layer of water. It's 2D, so there is basically something into the screen as well. And we worked in a NP lateral T ensemble, which means that we are applying a lateral pressure on our ice, on our 2D ice, and we had a confinement width. So the water-water interactions were treated using the machine learning potentials, while the water confining wall potential was basically a model Morse potential in this case, again, which has been a topic of investigation for a long, long time, right? So I'll quickly show you some of these results. So we found a very interesting phase diagram for 2D water. Uh, at low temperatures and low pressures, we find the familiar 2D version of the hexagonal ice phase. And as you increase the temperature, as you increase the pressure, you of course find you find denser phases. So pentagonal phase is something that we see. As you can see, even though the keen physicist who is interested in 2D systems would tell us that actually a uniform pentagon is not possible in 2D, but this is a deformed pentagon that we see. And after that, you have a region where a square phase is actually degenerate with this new rhombic phase that we found, and eventually the rhombic phase, which is also the densest phase, becomes the most stable phase. We find a highly non-monotonic dependence of the melting temperature, and these slopes also tell us that let's just like bulk ice, 2D ice also expands upon freezing. The other interesting bit were the disordered phases as you increase the temperature. And I don't think I will have time to go into the details of things, but all I will tell you is that somewhere, so you have a solid here and you have a liquid here, but we find something called a hexatic phase. And a hexatic phase is something in 2D physics, which is an intermediate between a solid and a liquid. It's something that is probed for 2D colloidal systems, as well as something which has been predicted by Thulis and et al., which has been predicted for systems operating with a short range two-dimensional potentials, for example, hard spheres and so on. And it was really interesting that something like water actually displays this phase, which like a liquid would rotate, but it doesn't really diffuse. So it's something in between. And of course, there are more rigorous ways of structurally probing the long range orientational order as well as the short range disorder, which I won't go into, but we have calculated all of these and presented in this paper in detail. The other thing that we find is that as we increase the pressure, we see a lot of dissociation. For example, the corresponding phase of bulk ice at 4 GPa and as a function of temperature doesn't really show any dissociation in a time scale of 100 picosecond, while monolayer ice at 2 and 3 and 4 GPa would actually show a lot of dissociation. So you see that in 100 picosecond, most of the water molecules actually dissociate. And actually, what we really found was that after calculating the ionic conductivity, that this really forms a super ionic phase at much more accessible conditions than bulk, because bulk water exhibits such levels of dissociation at, let's say, thousands of Kelvin of temperature and tens of GPAs of pressure, while we find this at much more accessible conditions. And just for you to see what the super ionic phase looks like, so this is a slow, and this is the last slide. This is a slow video where you see that a lot of proton defects are formed in this system, where instantaneously water molecules dissociate and an extra proton goes to the neighbor. And now we are going to see a fast forward of this, where we have removed all the hydrogens, but we are only showing a select few protons. And you see that in this phase, the water molecules are actually oscillating about their positions, but the protons are flowing through this oxygen lattice. And that is precisely the definition of a superionic phase, which is hypothetically found in extreme conditions like the interiors of giant planets. All right, so this is actually it, and I'm sorry if I exceeded a bit or if there is not much time left, but this is really what it shows. It that monolayer water, a seemingly simple system, has an extremely interesting phase diagram, and we hope that some of the phases like the hexatic phase and intermediate between a solid and a liquid and the superionic phase would have some room for future technology, especially in the regime of clean energy and energy storage materials. And hopefully this presentation also highlights the urgent need to develop accurate first principle methods, specifically combining machine learning. Thank you so much.
Let's thank the speaker.
Some acknowledgements. Yeah.
I think we have time for one question.
Hi, Venkat. Thanks a lot for your lovely talk. It's always nice to hear about structured water. This is, of course, a very old problem, and also in proteins and membranes, structured water plays a big role, like physiological role. And understanding structured water is important for knowing how the ions are transported across membranes. So I was just wondering, in the direction of this kind of research, I think interatomic potentials can provide a huge boost to this, because classical potentials really aren't accurate enough. But they do introduce more complexity, these kinds of problems, because of ions, solvated ions, and having solvation shells. And once you introduced ions into these structured waters, then things get even more complicated. So what is your opinion on the evolution of these methods towards more complex problems, biologically more complex problems?
Yeah, I mean, that's a really nice question, and certainly one of the most important topics, right, for water. How does it behave in our bodies? And yeah, I mean, so actually the next frontiers in this area are definitely to understand transport of ions in aqueous systems, both in bulk as well as in confinement. And a lot of research has been recently done to actually get these models to work in these cases, of course, ranging from simple baseline electrostatic models to explicit models with long range effects. So that's one of the prospects. The other thing, of course, with biological systems, you usually have many degrees of freedom and very large system sizes. So the way I would think about it is that one would also have to combine some sort of coarse graining approaches in these cases. Of course, first principle coarse graining approaches. So you have to probably coarse grain from your ab initio simulations so that you can treat these highly complicated systems. But I think most our community is taking some baby steps along these directions, and hopefully in the next few years there will be some solid papers where biological systems have been treated with machine learning potentials.
Thank you.
All right.
Let's thank Venkat again.
All right. Thank you so much. Yeah.
Next, we have an industry talk by Esa Puko.